Hello everyone. I am Bhavik Kumar Mahant from Department of Chemical Engineering, Indian Institute of Technology Madras, Chennai, India. Today I am presenting my oral presentation on application of sodium Pnictogen oxides in methane gas hydrate formation, experimental and modeling approach. This is the outline of my presentation. We will start from the introduction to gas hydrate, then troubleshooting for the gas hydrate challenges, objectives, gas hydrate experimental setup and results, introduction to ANN modeling, ANN model and result, conclusion and future perspectives. Now, introduction to gas hydrates. So, gas hydrates are a crystalline solid from water and gas molecules at a high pressure and low temperature in the presence of hydrogen bonding presence in the water. It is also known as a clatrate hydrate. Gas storage capacity of hydrate is phenomenal. Like 1 meter cube of hydrate can store up to 164 meter cube of gas at standard temperature and pressure in the presence of 0.9 meter cube of water. Now, these are some of the well-known structure of gas hydrate. In structure 1, cages of water, small water cages of 12 pentagon size and large water cages of 12 pentagon 2 hexagon combine together and form structure 1 in the presence of 46 H2O molecules that can be accommodate methane, ethane, carbon dioxide kind of gases. In the structure 2, small cages of 12 pentagon and large cages 12 pentagon and 4 hexagon can combine together in the presence of 136 H2O that can be stored small gas molecules like hydrogen, nitrogen and oxygen and the large molecules like propane and THF. If we talk about the structure H, then it can be made out of the small, medium as well as large cages of water and it can accommodate organic liquid in addition to gases. Now, background of research. Why we need to do research in the natural gas? Because research is going on the renewable and there is a very less scope of oil and conventional resources. If we talk about the last 140 years of data which is published from the British Petroleum Energy Outlook, you can see that coal has reduced its primary energy share from the energy sources and after 1980 petroleum and oil also reduced its share. Why? Because natural gas exploration and shale gas boom was started and it is predicted that gas is more cleaner fuel than oil and coal, so it has at least 40 to 50 years minimum requirement as a primary energy source in the future. If we talk about the latest data of past, future and present requirement, then you can see that natural gas requirement is continuously increasing in 21st century and it will be required as a primary energy source for at least for 40 to 50 years. So that's why natural gas is important for every economy to grow. Now, what are the different modes of transportation of natural gas? So if we talk about the large scale transportation, then it will be use liquefaction of natural gas and it can be transferred from the intercontinent from one liquid LNG plant to another LNG plant. But it can be inapplicable for small gas field as well as scattered users. So in the small scale transportation, we have CNG, compressed natural gas, but it has high pressure onboard cylinder, which is an inherent danger. And many a times we are heard about accidents occur due to CNG vehicles. Another thing is ANG, adsorbed natural gas. It is also good option, but it has a limitation in terms of absorption efficiency and temperature control. Now, if we talk about the natural gas hydrate, then it has a high storage capacity. It is less explosive in nature due to presence of water, and it is one of the most promising technology for future. So that's why we need to do research in the more for natural gas hydrate transportation for the transporting natural gas. Now, what are the challenges while we using the gas hydrate study? Generally, people are using chemical additive to increase the rate of formation of gas hydrate. Generally, gas and liquid interface has some mass transfer limitation while gas hydrate formation is taken place. So that's why some surfactant molecules like STS and CAPP can be used that can be converted into the micellar formation and that can reduce the surface tension at the interface and we can easily form gas hydrates. Now, what are the challenges in this kind of research? So first challenge is whenever we are using surfactant, it can create extreme amount of foaming. So it will be very difficult for us to use them for the scale up of the process. So here you can see in this video that whenever we release the natural gas or any methane gas from the gas hydrate formation in the presence of surfactant molecule, intense foaming will be there. So it will be difficult for scale up. So what are the troubleshooting for this kind of bottleneck problem in gas hydrate research? So first thing is people are doing research to generate some anti-foaming material which can reduce the amount of foam generated from the success surfactant molecule, and it can use for the scale up. But the major thing is this will increase the financial burden for the overall process. So what is the another alternative for this? So we need to select the chemical additive which has a property which for no foam generation, which is biodegradable in nature, which is origin from the natural resources, which can favor for recovery, reuse and recyclability of the experiments, which can economical in nature with high effectiveness. So we made our objectives for this study, like we need to select the suitable additive with desired properties of no foaming. We need to perform the gas hydrate formation experiment. We need to develop the artificial neural network based model for our experimental result. And then we need to compare the experimental modeling result and need to check the consistency of our model. Now, for experimental things, this is our experimental setup. In this is a high pressure crystallizer unit in which two polycarbonate windows are attached. So we can see the morphology of the gas hydrate. The temperature inside the gas hydrate reactor can be maintained by the external temperature control unit. The stirring can be provided with a magnetic stirrer. And as our temperature achieved in our gas hydrate reactor, we supplied the methane gas at around 50 bar and 1 degree centigrade, and the pressure and temperature data will be recorded from the controller and data acquisition unit that can be transmitted to data processing and computational unit, and we do our calculation of mole consumption into the computational unit. Now what are the results? So we are using two different types of chemical additives here, which is known as a salt of Pnictogen oxides 1 and salt of Pnictogen oxides 2. This is the mole consumption of methane gas data for both of that chemical additive over the period of 90 minutes. As you can see, this line gives the result for the pure water mole consumption, which is relatively low if we talk about our additive system, which are increasing the mole consumption in a relative amount of time. If we talk about the methane gas uptake, which is nothing but the mole of methane per mole of water, then we again achieve the similar kind of profile in that our mole uptake for our chemical additives is more than 0.015 mole for 90 minutes of time period, which is provided the tremendous amount of gas hydrate growth. Now, how can we check the morphology study of our gas hydrate? So this is the high resolution camera pictures taken from our reactor. As you can see, as time passes, you can see the crystallization of the gas hydrate formation is started, and at the end of the 1200 second, you can see the intense amount of crystal of gas hydrate formation, gas hydrate were formed, and due to in the presence of our chemical additives. So we can say that our chemical additives are promising in terms of the making the gas hydrate formation. Now, if we talk about result of our morphology study, then as you can see in the pure water, this is the data over the period of 60 minutes. Every 15 minutes we capture the photo, and that you can see it is a clear ice-like structure of methane gas hydrate. But if we talk about the SPO1 and SPO2, you can see at the end of the 60 minutes, there is a huge gas hydrate growth is available, and whole window are occupied with the gas hydrate formation within that period. So that's why we can say that our gas hydrate formation rate will be enhanced in the presence of these two chemical additives. Now, modeling using artificial neural network. So artificial neural network is a branch of artificial intelligence in which we are mimicking a biological neuron structure to a mathematical form. we have in biological neuron, information is received in the dendrite receptors. It can transmit to the end of the terminal section to the another neurons. The same mathematical function in the input variable and with weight, if we provide to mathematics and mathematical function, and if we can provide some very output result, then it can able to mimic our whole process of biological neuron. So in this process, basically input variable with the weights are given to the mathematical function, and then it will add some nonlinear element and we will get the result at output variable. So if we talk about the neuron structure available in our brain, so input if the same way in the mathematical INN model, input layer is combined with many number of hidden layer for providing the desired output results. Now, this is a methodology of ANN which we use for present work. We took the three parameters of our experiment, time, pressure, and temperature, and give as an input in our ANN model. And then it can pass us to the initial weights and biases. We use that initial weights and biases from the model and convert our mathematical model in MATLAB software. Then we substitute all our input values to it and get the output of it. And we compare our output of model prediction with our experimental result, and we check that our desired criteria is met or not. If it is met, then we can say that it is an optimized ANN model and we can use for our different screening of chemical additive. If it not met, and then we need to again do the same process. Now, model fitting result. If you can see for the pure water, model predictor mole consumption and experimental mole consumption are pretty much high in high. So as you can say, ask value is more than 0.95 for that. So it can say it is very well fitted with our experimental result. If we talk about the same optimized model for SPO1 and SPO2 0.0 then as you can see that for both of them we are getting the ask value more than 0.95, which is 0.969 and 0.9614. So and hence it can prove that our model can predict the experimental result very well. Now, what is the conclusion and future perspective? So we can use this as kinetic hydrate promoter has serious issue of forming, so which can restrict the scale up of this process. So we need to identify the chemical additives. In that we identify sodium salt of Pnictogen oxide as inexpensive, biodegradable, efficient and reliable alternative chemical additives. So we perform the gas hydrate formation with these SPOs and they prove them gas hydrate promoters in the great extent. ANN model was developed on the basis of input parameter as a temperature, pressure and time, and mole consumption as an output parameter. So the optimized ANN model which is in a good agreement with our experimental result. And another thing, we can use this ANN model for our future study for the screening of chemical additives without depending on the experimental study. And we need to pattern these SPOs in terms of use it as a kinetic hydrate promoter without form generation. Now these are some of the references which is used in this current study. And at the end, I want to acknowledge Indian Institute of Technology Madras for providing the research and analytical facility, Ministry of Education, Government of India for providing me the Prime Minister Research Fellowship, my PhD advisor, my research group, and last but not the least, my parents. These are some beautiful pictures of my campus. Thank you everyone for your patience.